So my paper was on effectiveness of mobile notification delivery. So to start with, notification recommendation is what I'm trying to do here. But as all of us know, that recommendation systems have been in existence for quite some time now, maybe a couple of decades at least. But the difference is that they have generally existed for movies or for restaurants recommendations, where typically the difference between notifications is that notifications are highly dynamic in nature, by which I mean that in a day one can receive probably 50 to 100 notifications potentially, whereas for movies maybe we watch only 1 or 2 movies in a day. So similarly for restaurants as well, like in a day we don't visit more than a couple of restaurants, whereas notifications can be 100 or even actually thousands. If you are actually an enterprise user, you may be getting thousands of notifications. So there needs to be there's a need for different kind of recommendation we believe about notifications. So another problem that we are trying to tackle in this paper is that there is a well-known problem which has been studied recently for like 7-8 years now, which is called the accuracy versus diversity problem for recommendation systems. What it basically means is that if we are recommending something with high accuracy, the accuracy is good, but then the diversity is lost. I'll try to demonstrate this with an example here. So if we look at these two figures here, the one on the left is actually showing IMDb list for when I search the movie The Scent of a Woman by Al Pacino. It shows the recommended list that if I watch that movie, what movies I should watch. There's a problem with this, if you can notice, that all these movies, one is Scarface, another one is A Dog Day Afternoon, etc. All these are Al Pacino movies. So you see, like, there's no diversity in that. It's good recommendation, it has a good accuracy. But then the problem is if we keep recommending it, research has shown that in a few days or maybe a few months, but definitely in some time, the users who are being recommended this will lose interest and then will start to become inactive users. The one on the right is also a recommendation, but it's a recommendation for fairly new movies. So we can see that when we search for Guardians of the Galaxy, which is an animation movie, you can say, or a superhero movie, the recommended list also contains similar movies of similar genre, but they are still a bit more diverse than the previous case, where the actors are different or maybe the directors are different. So it's not basically, it has more diversity in that sense, which is actually important because, like I said, research has shown that if you increase the diversity, only then you can retain the users. Otherwise, user retention becomes a big problem. So this is the motivation for what we are trying to do. We are trying to build a recommendation system for notifications, which is essentially different for cases like classical cases like movies. And the second problem is the accuracy versus diversity problem. So let me talk a bit about the mobile app that we are trying to study here. It's a app called the Apple Daily app. Actually, Apple Daily is a newspaper which was launched in Hong Kong back in 1995. And about 2004 or 2005, they launched their mobile application. And this is the mobile application that we are studying. So we got hold of some of their data. We actually had a collaboration with Apple Daily, so we got access to their data. We collected data for 2 months in 2016. And that's the data set that we have. This is the interface of how it looks like. On the left hand side, you can see a screenshot of the notifications, how it appears. So these are all different news notifications sent by the app. On the right side, we can see how the app interface looks like. So we can see that there are some categories of news, like highlights, finance, etc. And in total, there are 38 categories in the dataset that Apple really uses. And by default, like before we started to do the analysis, they were not using any kind of recommendation system as such. So they were basically sending notifications to users by randomly. So that actually provides us a good baseline of how to measure our performance. Like, so we can say that whether our system works or not against the default case. coming to the data set, it's a big data set where we have 50 plus attributes, out of which we choose about 12 of them for which are relevant for our studies. It has about 240 million records, and it is quite an extensive data set because we can see that about 1.8 million users use the app. However, only about 1.1 million are active users. By active, I mean they at least open one notification in the whole duration of the study. So the other 700,000 users are kind of inactive. So for all our analysis, we are doing the analysis based on these 1.1 million users who are active. And also, there's a geolocation data present for about half of the users, because when the users actually given the option of choosing whether they want to share their location or not. So about half of them choose to share their location, it turns out, and so we have the geolocation data as well for analysis. So we did a lot of statistical analysis, but I'm going to focus on the most important and relevant ones for this work that we did. It is based on a correlation-based analysis. So what we found is that if we select three parameters, which are the opening rate, notification opening rate, which is basically the number of notifications a user is opening divided by the number of notifications that it receives, right? So if we take that as a parameter, then second parameter is the response time for the notifications. So if a user is getting a notification, how long does it spend before it either rejects it or opens it? In both cases, it's basically the time to respond. Sometimes we ignore notification, so that we are not counting. We're counting the response time, which can be negative or positive, depending on whether the user is rejecting it or opening it. And the third parameter is the app opening volume. So users can open the app without notifications as well. Like you can think of a simple case of like Facebook. We don't always open Facebook app with notifications, right? We just click on the Facebook app when we want to browse. So users do that for this app as well. So that is the opening volume, with or without notifications, how many times the users are opening. So if we consider these three parameters, we found that there are some interesting correlations that we can find. The first one is that we found a positive correlation between the response time and the app opening volume. So if a user is having a less app opening volume, means the user is kind of less active. They also have a less response time, which is kind of unintuitive if you think about it, because we expect that an inactive user will have a high response time to notifications, but it turns out that it's the other way around. So that was something interesting. Also, the other way around, like most active users, they take a lot of time in opening or rejecting the notifications. And the reason maybe because the active users are probably not dependent on notification. So that's why they don't care about the notifications, they just ignore them. They open the app anyway without notifications. Second interesting result is that we found a negative correlation between the opening rate and the response time. So if a user is really having a high opening rate of notification, they generally have a less response time, which is expected actually, which is not like the previous case. It is intuitive. And the other way around, like inactive users are having high response times as well in terms of notification openers. And the third one is also a negative correlation we found between the app opening volume and the opening rates. So why these are important is, I'll explain this, but we are actually using these three correlations to build our model for recommendations. So now how do we optimize the notification delivery? The basic idea is that a good notification has to be one which has a high chance of being open. Right? So we are actually trying to build a simple model which can capture this characteristic without going into the high level, not high level, but like more complicated stuff like matrix factorization models where there is a lot of computation and it's kind of expensive to implement in a real-time scenario as well. Like I said, because notifications are highly dynamic, so we need to have a more, something which is more readily adaptable and simple to understand intuitively. This screenshot from another paper actually, which is studying on the Netflix data set. It also demonstrates the accuracy versus diversity problem I was talking about before. So if you see that as the number of days are passing, the Netflix database is actually getting more and more users, and they are getting them to vote more as well. But then the third graph shows that the number of active users are actually reducing, which is actually the diversity problem. So if you are keeping on recommending movies which are similar to your taste, you get actually bored. That's the core idea that I actually want to get across. That maybe recommendations can be good, but then for how long? That's the issue here. So we want to build a simple and intuitive model without going into tensor decompositions or matrix factorization, just to capture the basic idea and to make it more intuitive. So how do we optimize notifications now? I'll try to explain this question with a naive optimization framework. Why do I say naive is because it's just a basic formulation which will get across the idea, and then we can build upon the naive framework to make a better model as well. So if we, like I said, we had three parameters: the opening rate, the response time, and the ad hoc volume. So R and T will denote the response time, the opening rate and the response time. And let N be the maximum notification budget, which means that if for the company there is a maximum budget that they can send 100 notifications a day to a user, so that's the N. In theory, it can be variable, but in our case, in our implementation, we actually fixed it. We took it as N equals 1000. But it can be very theoretical. Then X is the optimal number of notifications that we should send. So what we are doing is, for each category, we are trying to evaluate these parameters. So for each category, what is the opening rate, what is the response time, and what is the optimal number of notifications we should send. So it's we are trying to build a contextual model, where context here means the the news category. So this is the basic formulation that we have here, which is actually optimizing two things. One is it's trying to maximize the opening rate, and the other is it's trying to minimize the response time, which is what we want to do actually, because we want to have a model where the users are opening more and more notifications and taking lesser time to open it than before. So it's a simple linear programming convex problem where if we take all the R's, all the opening rates in a vector, and then all the optimal number of notifications to be sent in a vector as well. If we take the parameter R transpose X, which is giving us the total number of not the total number, but amount of opening rate for all the categories that we are sending. So we're trying to maximize this parameter with respect to X, right? And then there are two constraints, which are that the maximum notification budget needs to be met. So the summation of all the X's needs to be N. So that is the first one, and the second one is an obvious constraint, which is the X greater than 0, because in real world we cannot have negative notifications. So similarly for the response time as well, the T transpose X should be minimized with respect to X again, with the same two constraints. Now, because these two problems have the same optimization variable, we can actually combine them using a weight, lambda, which is what we are doing here. So the actual naive optimization problem is the one on the right, R transpose X minus lambda T transpose X. We're trying to maximize this value. What lambda is doing is just giving us a weight of whether we want to focus on reducing the response time or want to maximize the opening rate. So if for your case you want to maximize the opening rate and you don't care much about the response time, you just make lambda small. And if you want to do the opposite, make lambda big. So in our case, for simplicity, we just took lambda equals 1, which is basically giving us equal weights for both of them. So we want to optimize both of them equally. And this is so if you solve the optimization, this is what we get. It's a simple LP, like I said, so we solved it using CVX. So this is the optimization result that we're getting. As I said in the beginning, there were 38 categories, but then without actually being much surprise, it's actually showing us only 2 categories to recommend. Notifications from only 2 categories. And one of them happens to be the category with the highest opening rate, and the other one is the category with the lowest response time. This is actually not surprising at all, because that's what we wanted the optimization to do actually in hindsight. And which is what I mean by the diversity problem, the accuracy versus diversity. This recommendation may be accurate, but then how useful it is, because we are just, out of 38 categories, we are only recommending 2 categories. So it's not very diverse at all, which means that users will definitely start losing interest. Because just imagine that maybe these 2 categories are like sports and finance. And if I only keep sending you sports and finance news, you will get ultimately bored pretty soon. And and stop using the app. So maybe it is accurate for some time, but then for how long? That's again the question. So we need to improve on this thing, the diversity part. So how do we do that? This is what our main first contribution is actually, which is the usefulness model. What we are doing is we are trying to define the usefulness of notifications. And as far as we know, nobody has quantified usefulness of notifications before. So I'm using three very simple models as a starting point to kind of quantify the usefulness of notification. So the first is the basic idea is that usefulness decreases as volume increases, right? In any given time interval. Maybe the time interval is 5 minutes, maybe 1 hour, maybe 1 week. But for any given time interval, beyond a certain threshold of number of notifications that you're sending, it becomes useless. That's the basic idea. So how do we express this idea? We are using these three basic models here. The first is a linear model where it's just decreasing as a function of x linearly. I'll explain what alpha is, but let's three models first. The second model is the quadratic model where the eta, the efficiency basically, or the usefulness is decreasing as a quadratic function, which you can see in the green line in the graphs. And the last one is the exponential model, where it's decreasing as the red curve in the figures. What alpha is here is, alpha is, you can say, the tolerance level of a user. So you have to model for each user separately, and it's a heuristic parameter as of now, the way we implemented in our research. So based on a user's history, you can find out whether the user is more tolerant or not. What I mean by tolerant is, how many notifications can you send to the user before he starts to get bored? So one easy way to demonstrate is, like, if you look at the figure on the right, in the linear model, we are sending 100 notifications before the usefulness is going to 0. Whereas on the right side, we are sending only 20 notifications and the user is already bored. So the usefulness has become 0. So we can say that the user on the right is actually less tolerant, much less tolerant, and the user on the left is very highly tolerant of notifications. So accordingly, we can define alpha for each user, depending on their history, like how much is their opening rate has been for the last couple of days, couple of months, whatever. And we can accordingly model alpha for different users. So thing is, if we look at the curves, we tried plotting the curves for all these three models for different alpha values, and for our case using the different R and T values. We found that the exponential model is the most flexible one actually, because if you look at these figures here, you can see the figure on the the curve for the exponential model, the red one, has actually the highest variance. Like it can be as close to a straight line, but it can also be very close to being almost a vertical drop. And so if you plot the function, you'll see that it's much more flexible than the quadratic model, which does not go below a certain. So that's why we feel that exponential model is the most flexible way to model different kinds of users. So if you identify users as tolerant or non-tolerant, they're most likely better model using this exponential model. So this is what we are actually doing in our model here. So so now all we need to do is, in the naive optimization problem, we just include this additional constraint that fix a certain usefulness threshold, that the usefulness should not go beyond or go below a certain value. And we just add the constraint. So now it's no longer a simple LP, it's a basically actually a non-convex problem, but then since we are fixing the usefulness values as pre-desired, that we don't want to go below a certain value. So if you fix that as a constant, then for each user it is, then it becomes a convex problem again. So now if we solve the convex problem, this is the allocation that we're getting actually, the one on the top. So if we compare it to the figure here, there are only 2 categories to recommend, but the new model actually shows us about 7 or 8 categories to recommend. So we have diversity here. We are losing a little bit maybe on accuracy, but then we have a lot of diversity here. So, and then if you look at the figures on the below, the 2 figures are showing the optimized allocation opening rate and the optimized allocations response time, which are actually on an average better than the default case. And overall, we are getting an increase of about 65% on the optimized model about the mean opening rate, and about 13% on the mean reaction time. So as a conclusion, we established meaningful correlations between opening rate, reaction time, and opening volume. Then we proposed a new way to quantify the usefulness of notification. Then using that, we proposed a complex optimization model which has these gains. And the basic idea is that the optimization is not actually micro-optimizing each and every category, so that we can see that it's sacrificing a few categories here and there, but then it's maximizing the more popular categories. So that's the basic idea of our paper. Thank you.